Okay, welcome everyone to lecture. First, a couple of announcements. Homework 1, search, is out. It's due next week, Monday. Just as a reminder, the way the homework works is that you go online, you can chat with other people about the questions, you can collaborate, but you have to submit your own answers. You can try any given question as many times as you like. The idea is that you get to work till you fully understand it, and then if you're willing to do that, you can get everything right. Project 1 will go out sometime probably really late tonight. Project 1 is your first real programming project. Don't consider Project 0 a programming project. It's just kind of a warm-up. It'll also be your first test whether you are prepared programming-wise for this class. So if you're worried about your programming skills and whether you should be taking the class, Project 1 is the time to try it out. It's longer than most projects, so start early enough. It'll be due next week, Friday at 5 p.m. Sections are starting this week. You can go to whatever section you like, but to keep things a little more manageable and have a little bit of anticipation of where people are going to show up, we posted a survey on Piazza. Please fill in the survey if you plan to come to section by tonight. The survey will close tonight at midnight. Go in, fill in what section you plan to go to, and that way you can have an idea of which sections are very crowded, which ones not, and maybe adjust accordingly. In fact, the survey shows you the results live. So the moment you go in, you can already see how many people intend to go to each of these other sections, at least the ones who have declared their intent in the survey, and you can already adapt accordingly. All right. Regular office hours have also started since this week, so if anything comes up, come and visit the GSIs or me, and any questions are welcome. Any questions about the logistics? Yes? Yes. 45 minutes ago it wasn't working, but a couple of minutes before I came in, it started working. So just in time to be able to announce that it's actually up. There were some edX permission issues that took a while to fix, in that it was visible to us, but not to students, but that's now fixed. Any other questions? Okay, let's start with today's lecture material then. Today we'll look at informed search. And before we get going on that, let's do a little overview and a recap of search. So informed search, what that means is we're going to somehow, when we expand our search tree, while we're growing it, use information about where the goal might be. That will be called heuristics. And that will guide us towards not expanding too much of the search tree to find a goal state. A first way we'll see how to use these heuristics is called greedy search. It won't necessarily be the best way, but it'll be an initial approach. And then we'll get to the pinnacle of this part of this two set of lectures, which is A-star search. This is really the algorithm we are working towards. And then, so far we've been looking at tree search, and sometimes in tree search, you re-expand the same state. You might have already seen the state through another path. You might expand it again. In graph search, we'll start avoiding that. Okay, so what was search? You started with a real-world problem, and you took an abstraction of all possible configurations of the real world, and that abstraction, all possible situations in this abstraction, are your states. Then, for a state, there's a set of actions available to you. Each of these actions have a cost associated with them. And there's a successor function that tells you, for a given action, what the next state will be. And then you have a start state, this is where the agent would start, and a goal test which checks for each state that you fit into it, whether it's the goal or not. There can be multiple goals. Then we have this data structure called a search tree. A search tree is a way of representing the search process. It's not the original problem formulation, it's a way of representing the solution method. The search tree has at the top the start state, and the nodes correspond to plans. partial paths that you hope will lead to the goal, right? These plans can have costs associated with them, and our search algorithm is, the difference between the search algorithms is how to build up this search tree. The search tree always exists, but you never want to build up the entire thing. And so different search algorithms will explore different parts of the search tree. The ordering in which you expand nodes in the fringe determines what part of a search tree you build up, and that determines how efficient your algorithm is. We said an algorithm was optimal if it's guaranteed to find the least cost path to a goal state. Okay, so a lot of the problems we've looked at so far were essentially pathing problems, but search problems are much more general than that. And so now we'll start looking at a different example, and this is the pancake problem. What's the problem here? You have a set of pancakes, and your task is to flip these pancakes to get the largest one at the bottom and the smallest one at the top nicely sorted. Okay, so in the first state shown here, you could squeeze in between there and just flip the top two, and you get this next state. You could put your spatula a little lower and get this next state, which is our goal state. Or you could put the spatula higher up, or all the way at the bottom, and you get this next state. So 3 possibilities of where you put your spatula, and accordingly, all pancakes above the spatula will flip over, reverse in order. So that's our action space and our state space. The cost could be, one thing you could say, how often I have to flip. We'll do something a little more sophisticated here, which is the number of pancakes that you flip. So if you take an action, that action requires you to lift 2 pancakes and flip them. That's a cost of 2. So the top action here is a cost of 2. The middle action has a cost of 3. And the bottom action has a cost of 4. Now, you might wonder, who cares about pancake flipping, aside from maybe some pancake flipping robots? Well, there are some people who have cared about this problem, and it might be the people you're least likely to think about. In fact, a pair of people you would not even think they would be thinking about things together. Those people are Bill Gates and Christos Papadimitriou. They wrote a paper about efficiently flipping pancakes, essentially. All right, so now it's justified we also care about pancake flipping. Let's look at the state space graph. This is the full state space graph. The arrows are bidirectional here, indicating that you can go in either direction. So you can flip them one way, flip the other way back. Our initial state could be, let's say, this one over here. Our goal state is this one over here. And then solving the problem means finding a path in this graph from start to goal. Solving the problem optimally means finding a path that has the minimal cost of all paths that reach the goal state. Okay, so here's the approach we've been looking at. Once you formalize a search problem, we have this algorithm called tree search. And what it does is essentially builds up the search tree until it finds a solution. So at the top, it'll put the start state. This is our start state. It'll call a successor function. This state has 3 successor nodes. So these are the 3 successor nodes. And it'll gradually expand the tree. Now it'll decide among these 3 nodes which is the next one to call the successor function on. For that, it has a strategy. We had depth first, which would look at the deepest node in the tree so far first. We had breadth first, which would look at the shallowest node first. And we had uniform cost, which would look at the cheapest node so far first. And as you go along, in this case, if you were to do uniform cost, you would prefer this one on the left over the one on the right. You'd build up this tree, and then at some point, you encounter a goal state, and you declare success. Critical in the way we specify this algorithm will become really important, especially as we work further along towards A-star search, is that you declare success only at the time you're willing to be ready to expand the node. So it says here, if the node contains a goal state, so choose a leaf node for expansion according to your strategy. If that leaf node contains a goal state, then you return the corresponding solution. So the time you declare success at is when you are deciding to take a node off the fringe. You're about to expand it, but you quickly first check whether it might already have reached the goal. And if it does, then you're done. OK. Now, this tree is the general representation of how search works, and it's probably the easiest thing to draw out. Implementation-wise, unification among all the algorithms we're looking at is something called a priority queue. And the idea here is that you'll have a data structure in your implementation. It'll be a priority queue. And when you insert something into the fringe, what that implementation-wise means is you are inserting something into the priority queue. And when you give it a priority, that priority will depend on your search strategy. So you insert a new node in the priority queue, associate a priority with that node based on depth for breadth first and depth first, or based on cost. And then when you ask a node to be expanded, the best one from the fringe, the priority queue will tell you what the best one is according to your priority scheme, which is what you choose. So one thing you might think, why a priority queue? It's nice, it unifies everything. It has a little bit of an overhead in that if you do DFS or BFS, you'll have a log n overhead. So it's slightly slower than the optimal implementations for DFS and BFS, because whenever you insert into a priority queue, you'll have a log n overhead. If you were to use a stack for DFS, you wouldn't have that overhead. If you were to use a regular queue for BFS, you wouldn't have that overhead. But logs are typically small numbers, and so in terms of implementation cost, you spending time implementing, it's probably the right strategy to go with a priority queue for all your search algorithms. And just change the type of priority depending on the algorithm you're implementing. OK, so uninformed search, which we covered last lecture, essentially started digging and didn't know where to go. It just kept track of where it was, what it had expanded, and kept going. What kind of picture that gave us in the case of uniform cost search was something like this. The part of a search tree that would be expanded before the goal was reached could look like this. At that point, this goal here could be reached. Right. Uniform cost search was optimal. Why was it optimal? It expands in the order of cost encountered so far. If you have expanded every path with a cost up to, let's say, C star, and the goal that you found has a cost C star, that means there's no cheaper path to the goal available anymore, because you've seen everything that has a cost less than C star. So it's optimal in the sense of finding the optimal path. But it's not very efficient necessarily, because it's kind of arbitrarily going down the tree based on what was expensive so far, not based on where it thinks the goal is. So let's illustrate this with an example. So what we'll look at here is uniform cost search in action. Uniform cost search in action on a very particular search problem. So what we have here is the empty waters. Green is the start state. Red is the goal state. And what you saw is the order in which uniform cost search is expanding nodes. So you see it radiates out from the start state, reaches the goal state at some point, but by the time it expands the goal state, it has seen everything that is within that distance from the start state. OK. Let's look at how that looks for Pacman. So we'll have a Pacman maze here. Not too fast. It ran very fast. So what are we looking at here? We have a maze where Pacman is shown is the start state. The goal for Pacman is to go from there to the 1-foot pellet. So it's a simple pathing problem. The red shows which states have been expanded. So the first time a state gets a successor function called on it, it becomes red. How red it becomes depends on how early on in the search that happens. So the more red, the earlier it happened in the search, the more it kind of fades towards black, the later it happened in the search. So what you see here is that in this maze, all but one state have been expanded in this search. So to reach the goal state, the search that happened had to explore every possible state except for one, just because the goal is far enough away that you can reach every other state within that number of actions. So it's very expensive. It's not guided at all towards where the goal really is, but it does find an optimal path to the goal. OK, so we'll want to have some kind of compass, something that indicates to us whether something is a good place to be a good place to be expanding nodes or a bad place to be expanding nodes. we'll call this heuristics. So one thing to keep in mind is that usually when you use the word heuristic, somebody will say, I have a heuristic for you. Before you cross the street in England, first look to the right, then to the left, then to the right. And that's a rule of thumb, right? That's the common way of using the word heuristic. It's not how we're going to use it in this class. This class is a very mathematical thing with a very precise definition. For us, a heuristic is something that, for every state, returns a number. Now, ideally, that number would be meaningful. But anything that returns a number for every state in your state space is a heuristic. The goal for us is to find heuristics and use heuristics that are meaningful and tell us something about how far away the goal is from that state. As opposed to everything we've seen so far, and most of what we'll see in the rest of this lecture, the heuristic is something that you have to design specific to your search problem. Right? Breadth first search, depth first search, uniform cost search, they're all just general algorithms. Once you have a search problem, it'll work. A heuristic is something that is very specific to the problem that you're trying to solve. So the way you picture this is your agent somehow has some metering system of how good a state is. There being in the red state, green being the goal, getting out of the maze there at the green arrow. Red is pretty bad, so the heuristic says, here it's a little better. The heuristic is in the yellow zone, and ideally that's the behavior heuristic would expose, right? Here is Pacman in a maze. What would be a reasonable heuristic here? What would be a reasonable way of measuring whether a state is promising to get to that bottom node? Yes? So one suggestion is distance to the dot. You know all the paths in the maze, and based on that, you say, how close am I to the dot? That heuristic will give you a lot of information. The downside of a heuristic is that you have to solve a pathing problem before you can use the heuristic. So it has a pro and a con. Any other suggestions? Yes? So Euclidean distance. So ignore the walls, because Euclidean distance you can just compute from coordinates. And so it's very quick to compute. You don't have to solve a search problem first. And it'll give you some estimate of how far away you are from the goal. So those are good suggestions. Here's another example, Manhattan distance. The reason to maybe use Manhattan distance rather than Euclidean distance is because we know Pacman can only move horizontally and vertically. And so Manhattan distance will be slightly more accurate than Euclidean distance. So here's an example. This would be 15. That's our first example heuristics. Manhattan distance, ignoring walls. Okay. So this is the Euclidean distance. It would be less. In some sense, it's less, which might sound good, but actually it means it's less informative in this particular case. Okay, let's look at another example. You're trying to, yes, question. Can the heuristic be a vector? Let's get back to that later. Towards the end of the lecture, we'll see how we can have multiple heuristics and what we can do about that. Let's look at another example. Here's our, let's get to the airport problem in Romania. Right? The airport is in Bucharest. That's where we need to be. Over here, we start in a rod, and we say, well, the real distance is going to be how much distance we travel along the roads, but we want something simpler, something that we can quickly compute and tells us how far away we might be from the goal, some estimate. And so one thing you could say is Euclidean distance, straight line distance. We know that there is no shorter path than the straight line between 2 points, right? So on this map, if we have the xy coordinates of each of the cities, it's very quick to compute the straight line distance. And so that would be the distances we get over here, and that's a reasonable heuristic function for this problem. How about for the pancake problem? This is to illustrate to you that it's not just about Euclidean distances and Manhattan distances. There's a lot more complicated problems out there that you need to design heuristics for if you're doing AI in the real world. What do you think here? Yes? So one suggestion is measure how well they are ordered. The top one here, 3 of them are in the correct order. That's a good sign, because if they're in the correct order, in this case we still need to flip them, but they're already in the correct order, so that we're close. We just need to do a flip. All right, there's many choices here. as you start thinking about these problems, you realize that you can spend a lot of time until you come up with really good heuristics, right? The example we put on the slide here is the largest pancake that is still out of place. Why is that? Let's say the largest pancake, there's 4 here. Let's say the largest one, specifically the largest one, is still out of place. What that means is, if it's out of place, it at least needs to move to the top some point, right, before we can flip them all over and get it at the bottom. And when we flip all of them over, we're flipping 4 of them. The cost is the number of pancakes we flip. And so if the largest one is still out of place, we have a cost of at least 4 to achieve the goal. Probably more, but at least 4. Similar reasoning is true for any of the other ones. If the second to largest one is out of place, you'll need it to get at least to, again, get it to the top, flip from there, flip at least 3 pancakes if the largest one's already in place, and so at least a cost of 3. So these heuristics can be pretty tricky. This is not even a great heuristic, right? This is just a heuristic that you could come up with. But it's really the tricky part in solving these problems. Now, let's see how we can use these heuristics. Let's say somebody gave you a heuristic that is where you should expand in your search tree. It tells you where to go, right? Let's see if we can use that. Here is our pathing problem in Romania. We're starting over here in a rod. We have our heuristic function over here. And what we'll do is we'll start our search, and as we run our search, we see that there's a path that runs over here that we might find at some point. There's a path that runs over here that we might find. And the interesting thing to notice here is that, let's say you are over here in Fagaras, right? After you expanded Sibiu, and let's say Fagaras and Riminicu Village are both on your fringe, and you're trying to decide between the 2 of them, the decision between the 2 of them will be decided based on this number here, 178 versus 193, which means that you'll go with this one first, because it has a lower heuristic value. Low is good because you want to minimize cost. And so you see, if you carefully look at what happens here with a search that goes lowest heuristic value first, which is greedy search, you'll expand along here and land in the goal that way. Once you land in the goal, greedy search will always right away pull the goal from the fringe, because at the goal you have a heuristic value of 0. You're already there. So you right away pull the goal, and that's it. So let's look at that in a little more detail next slide. But what you want to keep in mind here is that this is actually not the best path. It's a more expensive path than the lower path, but it will be what greedy search finds. So greedy search, expand the node that seems closest. Initially, one option, that's easy. You pick the one option. Then there are 3 options available. Pick the one with the lowest heuristic, Sibiu, looks most promising. Next one with the lowest heuristic, Fagaras. Next one with the lowest heuristic, Bucharest. At that point, your tree search says, I'm ready to expand Bucharest. It's actually a goal state, so I'm done. And you found a path to the goal very quickly, but not necessarily the best path. So the problem with these heuristics is that if they're very optimistic for certain cities compared to others, then you'll be guided along those. Another problem is that it doesn't account at all for how much cost you already incurred. If you're very close to the goal, that'll always be favorable, even if you follow the very expensive path to get there. So there's a couple of problems here with this greedy search, but at least it tries to use this heuristic information to guide where we expand in the search tree. So you find the wrong goal. We need to fix that. Here's a picture of what it looks like. The picture looks a lot like depth first search in that you kind of go down in the search tree towards some kind of direction. Unfortunately, it's not necessarily the right direction, but at least like depth first search, it doesn't just stripe left to right. If you're really lucky, it takes you right to the goal. The typical case, you're kind of somewhat in the direction of a goal and maybe the wrong goal. The worst case would look like this. And it's very easy to design heuristics that make this happen, right? How do you get this to happen? You just give everything a really low heuristic. Give everything a heuristic of 0. Except for states that are right next to the goal. And it's that way you keep your search away from the goals and you expand everything and at the very last, you finally get to the goal. So the quality of your heuristic will affect a lot how this search will behave. Yes? Okay, so that's a great point. So what you're getting at here is, you're saying, if I can rephrase it a little bit, is once you're in a certain situation in the pancake problem, where the biggest one is at the bottom, you know that one never has to move anymore. You just know that. You know the optimal solution never has to move that bottom pancake anymore. And you could exclude any action that would move it from your successor function, right? Because you wouldn't lose anything in terms of optimally reaching the goal. And so that's not something we call heuristics in this class. This is something else, but it's something else that can also help your search. And it's a way to have smaller successor functions, so less successors for a given state, based on your knowledge of what the optimality criteria are. And they're definitely very useful, but it's not what we'll call heuristics. Okay, so this is greedy search. Let's look at greedy search in action. So we'll again look at this empty water situation. Greedy search is trying to find a solution. The heuristic is just measuring the distance to the goal state. And let's see what happens. Boom. Straight to the goal. Works really well, right? We have a great heuristic here. There are no traps where things get stuck. And does the job fantastically. Let's now look at another problem. Let's go back to the Pacman problem and use greedy there. And we'll use the Manhattan distance to the goal state as our heuristic and see what greedy gives us. Okay, this ran very fast. What are we looking at again? Red means states that have been explored. The closer to black means the later it happened. The closer to just plain red means the earlier it happened in the search. So at first, it was over here, then over here, exploring these, here, 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 here. Then it went down this way in terms of which nodes it was expanding in the search tree. It was nodes that came down this path. Here it's turning the wrong way, but it's still going there because in terms of Manhattan distance, which is your heuristic here, these are the closest ones currently on the search tree. So you keep going here. Then you're out of those closed ones. Now here is a slightly further away one, but the closest now that's available on the fringe. So you expand here, 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 and so forth. And as you go along, you fairly quickly find a path to the goal. Let's compare this to the uniform cost search. Uniform cost search expanded every state except for the one all the way at the top here, because uniform cost search expands everything that is reachable with a cost less than the cheapest goal. So this is better that it expands less states, but still something's broken about it. Because the shortest path, the path we'd really like to find, would be to first move away from the goal. But of course, the heuristic value would go up moving in that direction, and so those states get very low priority in greedy search, and after moving away, coming back. So it's got some good properties, but it has its issues. What we're going to look at now, something called A-star search. It's really the pinnacle of our search algorithms. And what it's going to do is going to try to combine heuristics that we saw used in greedy search with the properties of uniform cost search that is get optimality. Now, let's illustrate it with a little cartoon. Many of you might have heard of the story of the tortoise and the hare. What's the story there? Well, the tortoise is this kind of steady but slow creature that finally gets to the goal. It's racing against this hare. The hare zips off right in the beginning, but kind of goes in the wrong direction and then arrives later, right? If you think of the algorithms we've looked at, tortoise is uniform cost search. Slow and steady, but finds the optimal way to get there. The hare is like greedy. It just zips off in a direction that looks good, but then it might not get there in the optimal way. What we really want to do looks like this. So what we're after is the steadiness of the tortoise, but the guidance of the hare to kind of give us a little bit of guidance where we might be headed. Stapling a tortoise and a hare together is not what we're actually going to do, but we're going to do this in computer science. So what do we have? We have an example graph here. This is a shortest path problem. Every edge has a cost associated with it, and every node in the graph has a heuristic value associated with it, which is its estimate of how far to get to the goal. Let's first look at uniform cost. Uniform cost will expand this order here. You go S, then when A is on the fringe, you'll expand A. It's the only choice. After having expanded A, B and E will be on the fringe. B, E, and D. Of those, B is most cheaply reachable, so B will be next, and then C will be next. So that's what uniform cost search starts out with. It's not the complete search, but that's the beginning of its search. Greedy orders by goal proximity. So it'll expand in the order of the heuristic value. Lower is better. Initially, the only option available is S, right? So S is on the fringe. Then A is on the fringe. When you expand A, you get the option, the choice between B, E, and D. E has a heuristic of 1, so that's next. Then it goes through D and into G. So that's the path it finds. It's guided towards the goal, but it's not following the right path to the goal, not the one we want. So you want to combine the best of both worlds here in A-star search. And the idea here is that rather than ordering by the cost so far, which we will call G, this is the backward cost. This is the cost uniform cost search uses. H, this is the forward cost. This is what Greedy uses. Forward cost, or our heuristic. Rather than just looking at one of them, we'll look at the sum of both. And this way, we can account for how costly it was to get to the current stage and how much we think it's going to cost from this state onwards to get to the goal. If we do that, we get this path here, and that's how it expands in the search tree. So this is what we want. Now, let's look at an example that illustrates one of the most critical aspects of how you implement this algorithm. Let's run A-star search for this graph. Initially, on our fringe, we have S, the start state. We have a backward cost. We'll have a state. Well, it's not really a state that we're looking for. We're looking for a plan so far. We have a backward cost, a forward cost, and then the total cost, which we'll call F. Initially, we just have S. The backward cost is 0. The forward cost H is 3. Total 3. There's only one on the fringe. That's our highest priority one. So we grab it out of the fringe, and then we add its successors. S to A, S to B. Then for S to A, we see that we have a backward cost of 2 and a heuristic value of 2 for a total of 4. For B, we have a backward cost of 2, a heuristic value of 1 for a total cost of 3. So SB is next. SB expansion gives us SBG. Okay. SBG has a backward cost of 5, a forward cost of 0, and a total cost of 5. At this point, we have a plan on our fringe that reaches the goal state. But our algorithm doesn't stop. Our algorithm doesn't declare success just because it found a way to reach the goal state. And this is critical. If it did, it would find a suboptimal solution here. The algorithm doesn't declare success yet. Our tree search says, let's wait. Let's just grab the next one from the fringe. Next one from the fringe is this one here. 4 is the lowest. And we get then, as a consequence, SAG with a backward cost of 4, forward cost of 0, total of 4. Again, it doesn't yet declare success. It just looks at the fringe, says what's the cheapest now. Cheapest F cost is this one here, SAG. It's ready for expansion. It realizes there's a goal state at the end, so there's no need to expand anymore, and it declares success. So it is critical that you only declare success at time that you would have expanded the node, not at the time you insert, because that would lead to suboptimality. Okay. Is A star optimal? We've built it up as this great thing. It's two animals bolted onto each other. I mean, this is good. Is it really that good? We haven't shown any properties of this algorithm. So let's see what it really can do for us. All right. Let's run this again on this graph here. Let's look at the fringe. We have initially just S. We have a backward cost G, forward cost H, total cost F. For starting state 0 backward cost, 7 forward cost, and 7 total. It's the only one on the fringe, so it's the one that comes out first. Instead, we'll get S to A, and we get S to G. S to A has backward cost of 1, forward cost of 6 for a total of 7. S to G has a backward cost of 5, forward cost of 0 for a total of 5. We don't declare success yet. We know that's not the right thing to do. Keep going. Which one's the next one to extract from the fringe? Well, this one here, S to G. We're ready to expand. We realize we reach a goal state. So we say, that's it. Tree search exits, says this is the path we found. S to G happens to have a cost of 5. That's a problem. Why is that a problem? Because the cheapest path is the one over here with a cost of 4. We did everything the way I described it. We followed the tree search algorithm perfectly. We used the priorities that I prescribed, but still we're not finding the correct solution. Why is that? In the back there, yes. Because the heuristic is bad. What's going on here? In A, there's this heuristic that says the forward cost estimate for A is 6. The real forward cost is 3. 6 is a lot worse. So it's extremely pessimistic. It makes you not consider that node for expansion, and now you missed it. Mathematically, the condition that we had here is that the actual cost to the goal was less than what we estimated. And that's the problem. Okay, so we need to be optimistic when we design our heuristics, right? You think of heuristics in two categories. There are the optimistic ones and pessimistic ones. The optimistic ones always underestimate. The property is there that from a given state, if you were to determine the cheapest path to a goal state, the heuristic is going to have even lower value, lower or equal. That's optimistic. All the other ones are the pessimistic ones, and those give you problems. Mathematically, here's what we need. Let's say H star n is the cheapest way of reaching the goal from a particular, when you already have a plan n, from there to reach the goal, the cheapest way is H star n. Then a heuristic H is admissible if it assigns a cost equal or lower than H star n. All our heuristics have to be bigger than 0. All our costs are bigger than 0. We'll not deal with negative costs here. Okay, let's look at some examples. How about this one that we looked at earlier, Manhattan distance? Is that admissible? Who says yes? Most people say yes. Why is it admissible? Well, it ignores the walls, right? You're computing the cheapest path for Pacman if there were no walls. That's always going to be a cheaper path than the cheapest path when there are walls. So this is admissible, it's optimistic. How about pancake flipping? Our heuristic there, we said the largest one that's out of place, the number of that pancake. So in this case it would be 4 because the number 4 pancake is out of place. Is that admissible? Yes, we discussed this earlier because we know that one at least has to first be at the top and then everything has to be flipped so it can go to the bottom, right? So we know it's admissible. Coming up with these heuristics is typically what you're going to spend your time on when you solve real-world problems, and making them admissible is critical. Now, we have this condition that we say heuristics have to be admissible. If not, we can show little graphs where A star already does the wrong thing. We haven't proven yet that it's enough, right? We've just shown if we're not admissible, things go wrong. We haven't shown that if we are admissible, things go right. So let's do that now. Let's show that indeed, if you have an admissible heuristic, A star tree search will give you the optimal solution. Here's a sketch of the search. This is our typical search tree. How could it go wrong? Well, it could go wrong if it, instead of finding the optimal path to a goal, it would find a path to another goal or a bad path to that goal. In the search tree, that means a different node that achieves the goal state. For it to go wrong, there has to be one of those. There has to be some kind of bad goal node in the search tree. There also has to be a better one, the one we really want. Otherwise, it didn't really go wrong. So G is the one we really wanted, the good goal node in the search tree. B is the bad one. And we're assuming, we're going to do a proof by contradiction. We're assuming things went wrong, right? So our claim is that G will always come off the fringe before B. That's our claim. If that's true, if G always comes off the fringe before B, then that means the good goal node gets popped before any bad goal node, which means we declare success with the right goal node, A star is optimal. Okay. Imagine this node B is on the fringe. Why can we assume that to be the case? If it's going to be popped to make things go wrong, at some point it has to be on the fringe. You can't be popped and declare success as a node before you've ever been on the fringe. At some point it has to be on the fringe if we want it to go wrong. So imagine there is such a bad goal node on the fringe. At the time that bad goal node is on the fringe, some ancestor of the good goal node has to be on the fringe. Why is that? You start your search. When you start your search, the start state is on the fringe. The start state connects to the good goal node. Otherwise, it wouldn't be a good goal node if you can't reach it, right? Then, when you expand the start state, you'll get some successors, and one of these successors will lead towards that good goal node. When you expand that one, it disappears, but one of its successors will lead to the good goal node, and so forth. So at all times, you'll keep a node on the fringe that is a partial path to the good goal node. Okay, now the claim is that this node that is also on the fringe at the same time as B will be pulled off the fringe before the bad goal node. Fn has to be less than or equal to Fg. Why is that? F, remember F is G plus H, right? Forward cost plus backward cost. For the node n, the F cost is the cost of reaching that node plus the heuristic. Our heuristic is assumed to be admissible, so it underestimates the true cost to the goal. So that means that overall n has to have a lower F value than G. Fg has to be less than or equal to Fb. Why is that? Well, for goal nodes, for Fg, it's equal to the cost of reaching G plus the heuristic at G. This is 0, so it doesn't matter. Fb is the cost of reaching B, well, of that getting to B plus the heuristic from there. Again, it's a goal, it's a bad goal, but it's a goal, so the heuristic is 0. This doesn't matter. And because we said B is a bad goal, the cost to get to no and to there is worse than the cost to get to G, which is the good goal. Okay. That means that because these two, if we combine these, we have Fn less than or equal to Fg less than or equal to Fb, which means that n, the node n will pop off the fringe before B, the bad goal node. This was just any n on the path to the good goal. We prove it for any n, which means it's true for all n. For any node n on the path to the goal, to the good goal, it will come off the fringe before the bad goal can come off the fringe. Well, if that's the case, then the good goal, which is also among those nodes, will come off the fringe before the bad goal. And that proves that A star search will always find the bad goal before, always find a good goal before it finds a bad goal. Yes? we assume H is admissible. So we assume H is admissible. It's always optimistic, underestimates the cost to the goal. If H is inadmissible, there's nothing we can prove here. Any other questions? Yes? You're saying this one here could be replaced by a strictly less? Yes. Because if it's really bad, really the one we don't want, it has to be strictly worse than the one we prefer. Yes? Okay, what does it mean optimal? Optimal means that the path you return is the shortest path. So for example, for this graph here, returning this path is optimal because that's a cost of 4. Returning this path is not optimal because it's a path with cost of 5. Your algorithm has a guarantee of optimality if no matter what search problem you feed into it, it'll return an optimal path, which is the cheapest one. Yes? Okay. Forward cost is the heuristic value. Backward cost is the cost you encountered so far. So you add up for all the actions that you've taken so far to get to that node. That's your backward cost. Yes? Say that again? What is the fringe? The fringe is the set of nodes that currently considered for expansion. It's the same as the priority queue you'll be maintaining. It's the bottom of the search tree, the nodes that you haven't expanded yet but are considering next. Yes? So the question there was, for every ancestor of G, we have that f of n equals G of n plus h of n. We know that h of n is smaller than or equal to h star n. And so we have that f of n is smaller than G of n plus h star of n, which is equal to G of G. Yes? Yes? Okay. Let's move on from the proof. Here's what it pictorially looks like to run. You have another question? We'll get to that in a couple of slides, but that will be very important. Yes? Here's what the picture looks like. Uniform cost search looks at all nodes where this is all nodes with f of n smaller than or equal to c star. Sorry, g of n. A star just looks at all the nodes with f of n smaller than or equal to c star, which will be a smaller set of nodes because your heuristic will typically be strictly positive. And so there's a smaller part of a search tree that you look at when you run A star search compared to uniform cost search. That's where you get the benefit. That's how heuristic is helping you. If you have a really good heuristic, you'll expand a very small part of that search tree. Okay, pictorially, in terms of states expanded, uniform cost search does something like this. A star search would do something like this. And let's actually see this in action. So here is, as a reminder, UCS in action. This This is again the waters. Green is the start state, red is the goal state. You get white dots popping up in the order of expansion of the states. That's uniform cost search. Now here as a heuristic for A star search, we use, just for illustration purposes, we use half the distance to the goal. We just use the distance to the goal. It's a little, the illustration isn't as pretty, so we use half the distance to the goal, which is optimistic, as our heuristic. And here's the node expansion we get. No, this is greedy. And then here is A star. Here we go. So that's really good, right? Why is it still expanding things over here? Well, it went all the way over here because as far as it is concerned, it just knows the cost encountered so far, which would be 3 for that particular state, reaching that state. And then it has its estimate of the cost to the goal, which in this case would be 3, 4, 5, something around 6, because it's half the measured distance. And so it would still be a relatively low F cost, still worth checking out according to the F criterion, right? But it doesn't go too far, and it mostly goes straight to the goal. Okay. A lot of the illustrations we look at are these pathing problems, because those are very good for illustration purposes, but keep in mind that A star is not about finding paths. It might be if you're programming the AI for StarCraft, which actually some people at Berkeley have been really good at. A couple years ago, there was a contest, and a Berkeley team led by Professor Dan Klein actually won the contest, was the world computer champion in StarCraft playing, and the pathing that happened in there was using A star search. But that's not the only application of A star search. Yes, pathing is great. There are many other applications. If you want to do resource planning, so how resources should move along to get some problem done. Robot motion planning. So you want a robot to move somewhere. How do you get the, what motor should move, how much to get the robot to get to a new situation that you like. A lot of problems in language use A star. And the search problems there are related to language analysis. For example, given a sentence, you're trying to search for the best parse into something like verb phrase, noun phrase, pronoun, and so forth, right? You might do it for machine translation. What you're doing there is you have a search problem, and there are many, many goal states. All the goal states correspond to possible translations of your sentence, but some translations are better than others. The best translation is the one with the lowest cost. It's the one where when you were trying to transform this sentence into the translated sentence, you incurred the lowest cost. And so then you have a search problem there to find that way of getting to the right translation. Speech recognition, same thing there. You get a sequence of essentially phonemes, or even before that, you get a sequence of essentially wavelets, which is just a continuous signal, and you somehow try to find a transformation into words. That transformation can be transformed into a search problem that we'll cover in lecture 20 or something. And the way that's solved most efficiently is using A star search. It's the same A star search we've already seen. What we haven't seen is how do you make speech recognition into a search problem, and we haven't seen how do you make a good heuristic for speech recognition problems. We already know the A star algorithm that you could run. Okay, before taking a break, let's look at kind of a review of the algorithms we've covered so far, and see what they look like. So this is uniform cost search. What you're looking at here at the bottom is the number of nodes expanded. They expanded 9,000 nodes. After expanding them, comes up with a really clever way of eating all the dots. All right? But it took a long time, a lot of thinking, because I had to explore a lot of nodes. Here's the same problem, eat all the dots, with A star search. Instead of 9,000 nodes expanded, it expanded 182 nodes by using a very clever heuristic. What is this heuristic, you might ask? That's up to you to figure out for your project 1. It's one of your questions. Okay. Now let's take a look at we'll do a little quiz here. What we'll do is we'll do a demo of a search algorithm, and you guys just shout out what search algorithm it is. Don't be shy. The louder, the better. All right? So before we get going, a little explanation. It's not just empty waters anymore. The dark blue is where there's an expensive cost. 3 times as expensive to move through the dark blue compared to the light blue. The white dots are still the order in which states were expanded during the search. And let's see what you think you see in action here. First one. PFS, why? It's just radiating out. It's completely ignoring the cost. It's just radiating out in all directions equally fast. Great. Next one. Same problem, different search strategy. A lot of people say uniform cost. Why uniform cost? What we see is it's radiating out somewhat equally, but much slower in the expensive parts, the deep waters, and much faster in the shallow waters, the light blue. Okay, here's another one. What's that one? People say greedy. Why greedy? Well, it doesn't really account for the cost it's already encountered. It just likes states that are close to the goal and keeps expanding those, ignoring the cost encountered so far. And so it goes essentially straight to the goal, but a very expensive path. How about this one? All right. That was DFS, yes. Gotta watch it before you call it out in these things, right? Last one. Might be able to call it ahead of time now. Was this one. A star, right? This is what we're really after. It explores somewhat equally initially, but then it realizes where the cheaper places are and continues along the cheaper route and goes to the goal pretty directly while ignoring most of the expensive states. All right, let's take a break here, and then we continue after the break with graph search and heuristic design. Okay, we're going to take a short break today because I want to try to get to the end here. So how about creating these heuristics? So as I said, most of the work we do when solving these problems in practice will be to create good heuristics. And we've talked about creating heuristics such as straight line distance, right? Manhattan distance ignoring walls. And the way you can prove that these are admissible is by showing that they solve a relaxed problem. And the idea here is that you say, I'm going to make a new problem. And that new problem, these successor functions have more successors. If you build a problem where your successor function have more successors than before, right, then that problem can only have a cheaper solution or equally cheap solution as the original problem, because you just have more options available to you. So for the first one, the idea is that now from every state, you can go straight line distance to the goal. That's how a new action that you made available in your relaxed problem. Now in this relaxed problem, the optimal solution is cheaper than the original problem. The other thing that's special about the relaxed problem is that it's very quick to find the optimal solution in a relaxed problem. Very easy to find the optimal solution. It's just going straight to the goal. It's that one new action you have available. That's optimal. So you have a relaxed problem, which means it'll give you a cheaper solution. And you need to pick a relaxed problem that's very quick to solve, so you can find the heuristic right away. For Pacman, the relaxed problem says you can go through walls. Now there are more solutions, so it's a relaxed problem. You have more options available, and it's very easy to solve. Because once you can go through walls, you can go horizontal, vertical, and you're at the goal. So those are the properties that we're looking for, and that way we can prove that our heuristic is indeed an admissible heuristic. You can also go the mathematical way and just show for every node, for every state in the system that indeed the heuristic is admissible by showing that it's cheaper than the optimal cost to the goal, but then you have to do some work that could be pretty tricky. Okay, why would you ever use an inadmissible heuristic? Well, you saw the difference between greedy search and A-star search, right? Greedy search was still faster through the deep waters. It found a not so great solution, but the running time was very fast. If you start using inadmissible heuristics, you kind of start interpolating between greedy and A-star, right? You have a heuristic that's too high, so you put too much weight on the heuristic, but it might speed up your search. And maybe that's what you need. Maybe you're happy with a solution that's not optimal, but is found very, very fast. And that could be the reason to sometimes use inadmissible heuristics. Okay, so let's look at another example. 8 puzzle. Who has played the 8 puzzle before? Great. 8 puzzle is like Angry Birds, right? It's a game you play when you're waiting somewhere in line. What are the states? Well, the states are all possible configurations of these tiles on the board. You can move these 8 tiles around, and then there's an empty spot, right? What are the actions? The actions is moving one of these tiles into the empty spot. So in the first state shown there, you have 4 actions available. How many states are there? Very many, right? The whole possible configurations on the board. How many successors from the start state here? 4. What should the cost be? Well, you can choose. But one option would be the cost is 1 for each time you slide a tile. And then the goal state is to get them nicely numbered as shown on the right. Okay. So how about designing some heuristics for this? A first heuristic we could look at is the number of tiles you misplaced at this point. Why is that a reasonable heuristic? Well, number of tiles misplaced. Every tile that's misplaced, you have to move at least once. Otherwise, it's not going to end up in the right spot. So it's a lower bound on the optimal number of actions to take to achieve the goal. What would it be for this particular state? You would count how many are out of place. It looks like all of them are out of place. So it would be 8. Then we could code this up, run uniform cost search, run A-star search with this heuristic, and we could see how many nodes were expanded. If the solution were 4 steps deep in the search tree, so problems that are relatively easy, we got on the average 112 for uniform cost search, 13 for A-star search with this heuristic, so much faster. If it's 8 deep in the tree, so the optimal path takes 8 shuffles, 6,300 for UCS, 39 for A-star. If it's 12 moves for the optimal solution, it's over 1 million, 3.6 million nodes expanded for uniform cost, 227 for A-star search. So it's a big improvement. It's a relaxed problem heuristic. How can we see it's a relaxed problem heuristic? Well, think about a new problem where you can actually move the tiles around more freely. You grab a tile and can put it into its target spot, and that's it. Thanks to this additional action, the heuristic you have is exactly computing the optimal solution in that new problem. Can we do better than this? What does it mean? What do I mean with doing better? Number of tiles misplaced is a reasonable estimate, but we know that ideally we get something that's close to the actual cost to get to the goal. That's most informative. So what can we do that's maybe better? Well, let's take a look at this one here. Consider the case where you take your puzzle, you now have an 8-level puzzle, and each of these tiles is moving on its own rails. So it's not blocked by other tiles. But you can still only move one at a time. In this relaxed problem, you can easily compute the solution. Every one of them just has to move as many times as it's out of place. You can add that up, and that gives you a new heuristic. It's the total distance for each one of them individually from their goal. Okay, let's see. Why is it admissible? Because we have a relaxed problem that corresponds to it. What's the heuristic for the start state? We have to count it out. Let's look at the difference in terms of nodes expanded. That's what we care about. This new heuristic, in this complicated case, goes down to 73 nodes. This was 12 steps deep. Uniform cost search took 3.6 million nodes expanded. For this heuristic, A-star search expands 73. That's it. How about using the actual cost as a heuristic? The actual optimal thing to do that has a cost, use that as your heuristic. Would it be admissible? Yes. It's smaller than or equal to the optimal cost because it's equal to it. Would we save on the number of nodes expanded? Yes, we would save a lot. It's guiding us in the right direction really, really well. What's wrong with it? Yeah, you solve the problem before you start solving your problem, right? Okay, so there's a trade-off here, and this is more generally true in that heuristics closer to the true cost are favorable during your search, but the problem is if they're expensive to compute, then your wall clock time might still be higher, even though it's in some sense a better heuristic because it's more expensive, overall time goes up. So while we're talking about different heuristics, right, what you can do is you can look at many heuristics for the same problem. And this is something that came up at the beginning. Let's say you have multiple heuristics. You can start comparing them. And we can draw a semi-lattice of the heuristics for a given problem. What does that mean, a semi-lattice? It's a mathematical word for a partial ordering. This here is a partial ordering. And what it is encoding is that if you are above another node, that means that for every state, your heuristic value is higher. Now, so if we have for every node n, HA of n is bigger than HC of n, then we have a relationship like this. Heuristic that's 0 everywhere is at the bottom in this partial ordering. And the heuristic that's exact, if we only consider the admissible heuristics, right, that's exact, sitting all the way at the top. This is bigger than every other admissible heuristic at every node. It's possible that heuristics are not comparable. In one node, A is bigger, and the other node, B is bigger, and the other way around, right? So what happens then is, in this partial ordering or semi-lattice, they don't have an edge connecting them. There's no clear ordering defined, so they're just sitting kind of next to each other. If you have two such heuristics that you can't strictly order, right, what you can do is you can compute the maximum. What that means is when you define a new heuristic, which we can call the heuristic HD, and HD, to compute HD, you compute HA and HB, then take the max, and that's HD. If you do that, you get a heuristic that's bigger than HA and HB in every node, bigger than or equal, because it's the max of the two of them. And so you're closer to the top. So if you have two heuristics, they're very incomparable, you can get a heuristic that's closer to the exact one by taking the max. You want to be as close as possible to the top in your A-star search to make it go as fast as possible, but you want to be careful that the computation of the heuristic doesn't start taking too long. So that's the trade-off. Okay, the one thing we haven't dealt with yet, and that is still slowing down our search, is that in this search tree, we're searching and searching, and we might encounter the same state a second time. And we're not keeping track of that. We're just expanding it again, doing the work again. All right? It's like navigating through a maze and seeing your own footprints again. That means you're about to do the same work again. It's not a good way to go. Here's a kind of simple example to illustrate this. This is a state graph here. We're going to draw the search tree. The search tree will look like this. Now, let's say you're searching. That means you're gradually building up this search tree. And you already did all the work here. And now you decide to go here and expand B. Then you know from looking at this problem, because this is the same state B as you had over here, that all the work you're going to do over here is going to be identical to the work you already did on the left. You're just duplicating work. We want to avoid that. We don't want to do the work twice. we should only go down one of these. Which one of them is the best is another question, and we need to make sure we pick the right one. But one of them is enough as long as we pick the right one. Okay, let's look at this for breadth-first search. Let's look at these circled nodes, right? We should never expand those in breadth-first search. Why? Let's look at E first. Why is it never useful to expand E? Because E is also sitting over here. Breadth-first search will have done E already up there. It's a better E than the one further down below on the left. And so this one is just useless to expand. This entire thing here is the same as this entire thing here. And it's not getting you anything because it's a worse part of the tree to be in. Similarly for the other circled nodes. They'll have equivalents that are strictly better. And the tree below them is just the same as below the other instantiation of that particular state. Okay, so here's graph search. The idea is you do tree search, but while you run tree search, whenever you expand, you call a successor function. You keep track of the states for which you call the successor function. You have a set. It's called the closed set. It means you don't look at those again in the future. So before you expand, you check if the state is in the closed set. If it is, you don't expand, you skip over it. So you never do the work a second time. This is important. Might sound as a detail, but if you implement it as a set, your code will be fast. If you implement it as a list, it'll be slow. Why would you ever implement it as a list? Because you could go talk to other people, or you could even talk to me, and I could have a lapse in the sense that almost everybody calls the closed list, even though it's not a list, it's a set. And so you'll often hear that phrase used, and people will then, as a consequence, implement it the wrong way. It's a set, and that's what you should use. Can it cause trouble? Well, we can worry about that, right? The first thing to worry about is completeness. Will we ever not find a path to the goal if paths to the goal exist? No, that's not a problem. Why not? The subtrees we just discard are subtrees that we're already looking at somewhere else. We're not losing a path. We're not losing the ability to find a path to the goal. We might just find a different path. How about optimality? Is it possible that now we don't find the optimal path to the goal? Well, I have to be careful about that, right? Because now the first time you expand the state, that's it for that state. So if the first time you reach that state, and the first time you then decided to expand it, was not the best way of reaching that state, that could be a problem. Because in the future, you're not going to deal with that state anymore. So it starts becoming important that the first time you expand the state, that you reached it optimally. Otherwise, you're going to be in trouble. Code-wise, this is all that happens. Tree search was all the code except for the code in this box here. You just have an additional check where you check whether a state has already been expanded or not. Okay, let's look at how this could go wrong. Right? State space graph here. We have some heuristic values. We have a search tree. Start state, 0 plus 2. 0 backward cost, 2 forward cost. We expand. We have a closed set, which has S in it now. Then we have A and B. What do we pick next? B, because that's cheaper. That means B goes in our closed list, closed set. There you had it. Which one's the cheapest now? C. Expand C. C goes into our closed set. What's cheapest now? A. So we go with A. A will go in our closed set. What's cheapest now? C. This C over here is already in our closed set. So we actually don't even bother. We don't consider this C. That's a real pity. This C is cheaper than the C we looked at before. But we already looked at C before, and so we're not looking at it again, not expanding it again. What's cheapest now on the fringe? There's only one thing on the fringe, which is G. And this is the solution we find. A-star graph search. We don't duplicate work in this case, but not optimal anymore, because first time we saw C and expanded it, it's not the best way to reach C. Tree search would have kept going, would have found this other way of reaching the goal. I'm going to take questions after lecture. Okay, so what was the problem here? The problem here is that you were looking at A. The heuristic of A was 4, which was very high. As a consequence, we weren't considering A. And we reached C through another state. It was a more expensive way of reaching C, but that other path looked more promising. And so A star was going there first, what looked promising, getting to C, putting it in a closed set, and now you can't get through it here anymore. That was the problem, right? So really what's the problem here is that somehow this is too high relative to what we have over here. We have this thing that looks kind of, oh, this doesn't look too good. And then after you expand, you realize, actually, this was better than I thought. And that process is what makes it go wrong here. So the condition we impose to make graph search work is something called consistency. And it's this definition over here. If that definition holds true, then what you have is that the real cost will be higher than the cost implied by the heuristic for just the triple of nodes that you're considering here, A and C, and then the goal state. And this could be any two nodes, any two states, and the goal state. What happens if you run A star with a consistent heuristic, and this is the crux of the whole process, maybe the most important thing to understand about A star graph search with a consistent heuristic is that you build your search tree. As you build your search tree, anytime you expand a node, that node has the cheapest F value. We know that. That's what we do. And after expansion, because of this condition over here on your heuristic, after expansion, everything that comes into your tree has a higher F value than what you just took off. That's really the key here. This condition ensures that after expansion, what you put on will have a higher F value than what you had on it before. And that ensures you never kind of get stuck along a path where something looks bad, and then if you were to continue, it starts looking better. That's what was causing trouble. The consistency ensures that that never happens. It ensures that things always get higher and higher F values as you work through the tree. And because they always get higher and higher F values, it also means when you expand a particular node and you expand the state for the first time, never in the future will that state appear in the tree with a lower F value. Because when you expand with a certain F value, in the future, everything will have a higher F value. So that means when you expand for a particular node, you're safe. Nothing in the future is going to be cheaper than what was currently on the fringe in terms of F value. So you'll never have this wrong way of reaching the node win out if you have a consistent heuristic. So as a consequence, this is a proof sketch, not a formal proof, but that's the intuition. F values keep increasing as you run your algorithm, so you never expand too soon. So this is the summary of optimality. You can take a look at that. To wrap it up, key here is what we did today. We put a tortoise and a hare together, and we got our A-star algorithm, which is what we're going to use for most real problems. That's it for today. Thanks.